Hello, dear students. I am Muhammad Asif. Hope you are enjoying happy and good life. We are going to discuss our second lecture of the chapter Ammonia and its uses. In the previous lecture, we have studied how in the atmosphere the percentage of nitrogen remains constant, and that was due to the nitrogen cycle. Now, in our second lecture, we are going to discuss the industrial manufacture of ammonia. Industrial, as ammonia is enriched with the largest percentage of nitrogen that can be provided quite easily to the soil. That's why ammonia is a very important chemical which is used as a fertilizer alone or in combination with the different salts. The industrial manufacturing of ammonia is called Haber process. Actually, Haber process was introduced by a German chemist, Fritz Haber. Initially, the production of the ammonia was used to produce explosive material by the Germans in Second World War, because the explosive material supply was banned by the Allies for the Germans. That's why Fritz Haber introduced the production method of ammonia for the use as an explosive material. But later on, nowadays, as ammonia is having a maximum percentage of nitrogen, that's why it is used as a fertilizer. What were the raw materials? The raw material for the Haber process was number one, hydrogen gas, H2, and second, nitrogen gas, N2. The first gas, hydrogen gas, is obtained in bulk quantity from the cracking of petroleum. Cracking of petroleum. For example, if we have ethane, and if we crack this molecule thermally in the absence of air, then this molecule can be transformed easily into ethene molecule and hydrogen gas. No doubt this is also a gas. Now, this is the cracking process of petroleum. As a result of cracking of petroleum, we can get hydrogen gas, and this hydrogen gas is then utilized in the Haber process for the production of ammonia. This is also important method and easy and cheap source to obtain hydrogen gas, because in petroleum industry the 50% of heavier hydrocarbon molecules are thermally cracked to make them useful with the lower boiling points, and during the cracking process we get hydrogen gas, and this hydrogen gas is then utilized for the production of ammonia gas. The second gas, nitrogen gas, is obtained from air. As we know, that air contains 78%, air contains 78% nitrogen, and then it contains also 21% oxygen and 0.04% carbon dioxide. This is the overall composition of air. If we pass this air through a solution of alkali, solution, then what will happen? Both of these, nitrogen and oxygen, are neutral gases, while carbon dioxide is acidic gas. Whenever we will pass all of these gases through this alkaline solution, carbon dioxide will be trapped, producing respective carbonates, and then we can easily get nitrogen and oxygen gases. Now from this, it is quite easy. We can liquefy both of these gases. When both of these gases become liquid, then by the fractional distillation we can easily separate out nitrogen from the oxygen. Another alternative method is, if there is a mixture of nitrogen and oxygen, and if we burn hydrogen gas in this gaseous mixture, automatically hydrogen and oxygen will react together, producing water molecule, and the nitrogen gas will be left behind. If we decrease the temperature, water molecule will be liquefied quite easily, leaving behind nitrogen, and from this nitrogen gas collected can be used here for the industrial preparation of ammonia. Now, the Haber process equation for the preparation of ammonia is, it is a reversible reaction. Nitrogen gas reacts with hydrogen gas and produce ammonia gas. The condition of this reaction are, we keep 450 degrees centigrade, which is a compromised temperature. Why it is compromised temperature? Because this reaction is exothermic reaction itself. This is exothermic reaction. Heat energy is produced. No doubt, lower temperature will favor the formation of ammonia, but still we keep 450 degrees centigrade temperature. Why? Because if we decrease the temperature too much, just to increase the yield of ammonia, but at a lower temperature the rate of reaction will become too slow, due to which the overall process will become uneconomical. That's why, keeping in mind the reaction is exothermic, still we maintain the temperature about 450 degrees centigrade to keep the rate of reaction at a certain level to produce ammonia. Second is, we use 200 atmospheric pressure. We know that according to Boyle's law, if we increase the pressure, the volume of the gas will decrease. If we look at this equation, the total volume, one volume of nitrogen reacts with 3 volume of hydrogen. Total are 4 volumes. These are the volumes of reactants. While the 2 volumes of ammonia are going to be produced from these 4 volumes. Now this is quite clear. If we will increase the pressure, the gases will decrease their volume and definitely they will transform into that compound which is occupying lesser volume. Automatically from 4 to 2 volume transformation will take place quite easily at 200 atmospheric pressure. Means the high pressure will favor the formation of ammonia and will compel the reaction to move in the forward direction. Both of these conditions are accompanied with the use of catalyst. In this Haber process, iron is used as catalyst and iron 3 oxide is used as promoter. Promoter means that substance which increase the activity of a catalyst, which increase the catalytic efficiency of a catalyst, that is called as a promoter. In the Haber process, iron is catalyst and iron 3 oxide is used as promoter. Now, both of these conditions of temperature and pressure are in alignment with these catalyst and promoter. If we want to change, these conditions are the optimum conditions, best conditions which is experimentally proved for the Haber process. When ammonia gas is produced, then we know that from this equation, nitrogen is nonpolar gas, hydrogen is nonpolar gas, but ammonia is a polar molecule. So, it is quite clear from their polarity, lesser amount is absorbed to break the bonds of reactants, because the non-polar or weaker bonds are going to break, while in case of ammonia the polar molecules means stronger bonds are going to be formed, as a result of which too much amount of energy is released, due to which this Haber process becomes exothermic. Again, if we decrease the temperature of the reaction mixture, then at minus 34 degrees centigrade, at minus 34 degrees centigrade, ammonia gas will be liquefied, while hydrogen and nitrogen gases will not be liquefied, because in ammonia molecules, due to polarity, a hydrogen bonding is created between ammonia molecule, due to which ammonia liquefy easily at minus 34 degrees centigrade. While on the other hand, No such forces are created in nitrogen molecules themselves and hydrogen molecules themselves. That's why both of these will remain in the gaseous form while ammonia will be liquefied at minus 34 degrees centigrade. Then non-reacted gases again recycled in the process to avoid the wastage of the gases. That's why due to the cyclic process, the non-converted gases are again and again recycled through the process. As I have explained, this is a reversible reaction. Reversible reactions are those reactions which can proceed in both forward and backward reaction. So, in such cases, when the reactants and products are also present in the gaseous state, the effect of temperature and pressure become more prominent. For the exothermic reaction, low temperature is favorable to get the maximum yield, but the too much low temperature, as I have already explained, slower down the rate of reaction too much, making the whole process uneconomical. On the similar ground, 200 atmospheric pressure is used just to keep the reaction moving in the forward direction and to prevent the reaction to be converted back into hydrogen and oxygen. That's why we apply high pressure. High pressure will move the reaction in the forward direction. If we plot a graph for the efficiency and showing the relation with temperature and pressure, we can show the graph just like this. Just like this. If x-axis there is a pressure, say this is 0, then 100, 200, 300, 400, 500 and then 600. This is atmospheric pressure. Atmospheric pressure. And then if this is percentage yield, 10, 20, 30, 40, 50, this is a percentage yield. The graph comes just like this. At 600 degrees centigrade, this curve will be obtained. At 500, this curve will be obtained. And at 400, this curve will be obtained. This graph is also indicating that as the pressure is increasing, then at varying temperature, the percentage yield is different. If we will increase the temperature too much beyond 450 degrees centigrade, this will prove the drop in yield. If we will decrease the temperature due to its exothermic nature, the low temperature will favor, and this graph is indicating this fact that at the same pressure, by just only decreasing the temperature, the percentage yield will be increased. While at 4 degrees centigrade is this much yield. But at 4 degrees centigrade the reactions become slow. That's why normally we take the say 450 degrees centigrade, and at 450 degrees centigrade and at 300 atmospheric pressure, what will be the percentage yield? The percentage yield will be just like this. Might be 40 or 41 or 42%. That can vary, varying the temperature and pressure. As the process is exothermic itself. No doubt, low temperature will favor it. But as I have already explained that at a very low temperature, the rate of reaction will become very much slow. I have explained all the concepts, raw material, nature of the chemical reaction, and then effect of the different parameters, temperature, pressure, and catalyst. Now, the catalysts are the substances which reduces the time, which reduces the cost of production. That's why the catalyst save our energy and time, both. Whenever we are performing the chemical reaction without catalyst, too much time and too much energy is utilized. In case of Haber process, 450 degree centigrade, 200 atmosphere pressure, and iron 3 oxide, these are the optimum conditions at which the percentage yield of ammonia is observed to be the best. I hope you have understood whole of this concept of Haber process. If you have any question, you can leave the question